Fundamentals of Physics, my video lecture series. This is talk number 15. We will continue our discussion about kinematics. Earlier also we have discussed kinematics in 1, 2 and 3 dimension in this series. Today we will focus on kinematics in 3 dimension, and later in this talk we will discuss relative motion. To describe the kinematics of a particle in 3 dimension, we have to describe the 3-dimensional Cartesian space, and for that we will have to make a choice of x, y and z axes and the unit vectors along the x, y and z directions as described earlier. Any point can be taken as origin and any direction can be taken as x-axis. Since we are adopting right-handed coordinate systems in our discussion as a convention, therefore once an x-axis is chosen and a particular plane is chosen called xy plane, then the y-axis will be at 90 degrees anti-clockwise to the x-axis in that xy plane, and z-axis will be given by the right hand screw rule and will be perpendicular to the xy plane. And if you rotate a right-handed screw in the direction from x to y, then the direction in which the screw advances when it is held perpendicular to the plane will be called the positive z direction. Let us use I cap for unit vector along x-axis, j cap for unit vector along y-axis and k cap for the unit vector along z-axis. Any point in 3-dimensional Cartesian space like described here, this point P is having coordinates x, y and z. So either we can describe the point P by specifying its coordinate or by specifying what we call the position vector. Position vector of the point P having coordinate x, y, z will be given by r vector equal to x I cap plus y j cap plus z k cap. So in this manner, position of the particle in 3-dimensional space can be specified. At each instant of time, it will be located at a particular point, and in general therefore the x, y and z coordinates are function of time, and so is the position vector r vector is a function of time. With change in time, the position may change unless the particle is in the state of rest in the chosen frame of reference. So we have defined the velocity vector earlier as the first differential coefficient of the position vector with respect to time. So v by definition is dr by dt, and which we can express in terms of its component dx dt, dx by dt I cap plus dy by dt j cap plus dz by dt k cap, where dx by dt would be called the x component of the velocity vx, dy by dt would be called the y component of the velocity vy, and dz by dt will be called the z component of the velocity vz. And so if you know the coordinates x, y and z as function of time, then by differentiating you can obtain vx, vy and vz that we have learned in past lectures. And velocity is a vector quantity and it is having 3 components x, y and z, just like the position vector. The velocity vector can be written as vx I cap plus vy j cap plus vz k cap, and then we can extend it to higher derivatives. For example, the acceleration would be defined as the rate of change of velocity vector with respect to time, and therefore the x component of the acceleration ax will be equal to the rate of change of vx with respect to time, or the second rate of change or second differential coefficient of x coordinate with respect to time. And similarly we can interpret ay as dvy by dt or d square y by dt square, and az as dvz by dt and d square z by dt square. So acceleration is also a three-dimensional vector like velocity vector and the position vector. And the higher derivatives which we have defined earlier for one dimension can also be defined in the same manner. You can define the jerk as the derivative of acceleration vector with respect to time, and jerk will be a vector quantity. And then the snap as the derivative of jerk vector with respect to time, and so on. The crackle and pop could also be defined. So it's a very simple generalization which we have learned in the past few lectures. So we know that in three dimension the vector quantities like the position vector, velocity vector or acceleration vector or higher derivatives, which means all the kinematic quantities which we have defined are vector quantities. Each of these vector quantity will be having three components, one along the x-axis which you can call either as x component or the projection of the quantity along the x-axis, and similarly you can describe the y component as projection of the vector along the y-axis and z component as the projection of the particular vector quantity along the z-axis. So we have learned this language by now, and now we also understand that in three dimension the two spatial cases which we have discussed are in fact three. The state of rest means that the position vector is independent of time. The particle remain at the same point p where it is located for all instant of time, and the velocity, acceleration, jerk, snap and all other higher derivatives have zero value. And the state of rest is defined therefore by r vector equal to a constant vector, velocity vector equal to 0, acceleration vector equal to 0 vector or null vector, and so on. The spatial case of uniform motion, the acceleration vector will have the value 0 or null vector, so acceleration is equal to null vector, and the velocity vector v vector would be a constant and would be independent of time. So to describe that velocity, I have used here the symbol u cap, u vector, and u vector can be expressed in terms of its component x, y and z like ux, uy and uz. So you can write that the velocity is equal to or equivalent to u vector, and which is equals to ux I cap plus uy j cap plus uz k cap, and is constant, thereby meaning each ux, uy and uz are constant. Each of this is constant, and therefore we can write that by integrating the velocity vector we can obtain the position vector. And in the last case we have shown that we can also define the displacement. So if you know the position vector at time t equal to 0 is r0, then the displacement vector in time t equal to 0 to time t equal to t, at t equal to 0 the position vector is given by r0 vector, and at t equal to t the position vector is given by r vector. Then the s vector, which is called displacement vector, is nothing but r vector minus r0 vector, and therefore is equals to the u vector into time, and so u vector times t. So we can express the expressions in vector form in three dimension also. And similarly we can discuss the uniform acceleration cases in three dimension. The acceleration would be constant. I am not introducing new symbol, and I assume that when we discuss uniform acceleration and when acceleration is resolved into the components like ax, ay and az, acceleration equal to constant would mean ax is constant independent of time, so is ay independent of time, and az will also be independent of time. And so when acceleration is constant, all these three numbers ax, ay and az will have unit of acceleration meter per second square, dimension of acceleration, but will remain constant and will not be changing with the time. And we can derive in the same manner all the Newton's equations which I have discussed for one dimension and two dimension in detail, and here I am reproducing the same set of equation. So the first equation, velocity vector at any instant t, so v is equals to vector u plus vector a times t. So v equals to u plus at. Every time I will not speak vector, and this arrow used in the transparency of PowerPoint slides is indicating that the quantity is a vector quantity. So v vector is equals to u vector plus a vector times t is the first Newton's equation, and similarly the other Newton's equations are given here. In the first equation, the displacement vector is missing. In the second equation, the displacement vector s, which is equal to r minus r0, is given by ut plus half at square, where s, u, a, r and r0 are vector quantities. The third equation can be obtained from the first equation by taking the dot product of v with itself, and one can show that v dot v is equals to u dot u plus 2 acceleration dot s, the displacement vector. And similarly, by replacing the u from the first equation, you can obtain the equation, fourth equation, from the equation number 2, and that reads therefore s equals to vt minus half at square. So in this equation u is missing. In the equation number 3rd, time t scalar parameter is missing, and similarly by adding the equation 2nd and 4th, we can get the 5th equation. I have already explained that by using the given information, if 3 quantities are given out of the 5 vector quantities and time, so 4 vector quantities and time involved here in this expression, if 3 are given and 1 is missing, then the corresponding equation can be used to determine the 4th. So the 5th I am calling the missing. So if the displacement vector is missing, then the first expression should be used for solving numerical questions that we have discussed. All this equation you must remember for the case of uniform acceleration, whether it is in 1 dimension or it is in 2 dimension or it is in 3 dimension, these equations would be valid, because now we have generalized this equation for 3 dimension. The 1 and 2 dimension cases can also be obtained from 3 dimensions by respectively considering only that components which are involved in the quantities. So I consider an example here just to revise our understanding, and the example is not of uniform acceleration or uniform motion or state of rest. This I have chosen for a variable acceleration. So when acceleration is dependent on the function of time, the numerical question is taken, and similar question was taken earlier for the 1 dimension also. Now suppose position vector of a particle is given by this relationship. R vector is a t raised to power 3 I cap plus b t square j cap plus c t k cap. So a t cube I cap plus b t square j cap plus c t times k cap. So where the value of a, since a t cube must have the dimension of position or length, so as explained earlier in dimension analysis, the unit of a will be meter per cubic second, and the value of a is given here up to 3 significant figures, 2.00, and similarly the value of b is given up to 3 significant figure as 1.75, and the unit would be meter per second square, because bt square should have the dimension of length, and the ct should also have dimension of length. So the c will have a unit of meter per second, and the value is again given up to 3 significant figures. All quantities, the constants a, b and c have been specified up to 3 significant figure in this case. And so find velocity and acceleration at t equal to, and it is better to write 2.00 second and t equal to 4.00 second. Find displacement and average velocity in this time interval, t equal to 1.00 second and t equal to 3.00 second. Here I have mentioned t equal to 2 second and t equal to 4 second, but this should be interpreted with 3 significant figures, because in the latter calculation I have used 3 significant figures. So sometimes the quantities are given in this manner. For simplicity, we do not specify these significant figures correctly, but one should understand. So I am here taking t equal to 2 second as t equal to 2.00 second, and therefore the three significant figures, the time is also known. And by differentiation with respect to the time from the position vector r vector, which is given here, now it's very easy exercise for you. You know that the differentiation of t cube is 3t square. So you have on the differentiation of the position vector with respect to time, the x component here is a t cube. So x component of the velocity will be 3at square. Y component of the position vector is bt square. Since differentiation of t square is 2t, so y component of the velocity will be 2bt, and the z component is ct, and since the differentiation of t is 1, so the velocity z component will be c, and therefore the velocity vector will read 3at square I cap plus 2bt j cap plus c k cap. And acceleration can be further obtained by differentiating this velocity vector with respect to time, and we get therefore 3at square I cap would give you 6at I cap because differentiation of t square is 2t, and 2bt j cap would give you 2b j cap because differentiation of t with respect to t is 1, and the third quantity, the z component, is ck, is constant in the velocity vector, and therefore there is no acceleration in z direction in the expression which we have obtained, because the differentiation of ck would be 0. Differentiation of constant with respect to time is 0. Now once you have obtained the expression of velocity and the acceleration by using the given expression of the position vector which we have done here, we can find the value at any instant of these quantities. And so this is a very simple numerical calculation to check that the velocity at t equal to 2 would be given by substituting the 2 for the value of t in this expression, and that turns out to be 24 I cap plus 7 j cap plus 3.14 k cap. Each I have specified with three significant figures. So I should read 24.0 I cap plus 7.00 j cap plus 3.14 k cap. And similarly, the velocity at t equal to 4 is obtained by substituting 4 for the value of t, and that we get 96.0 I cap plus 14.00 j cap plus 3.14 k cap. And acceleration would be obtained by this expression, and acceleration at instant t equal to 2 is therefore equal to 24.0 I cap plus 3.50 j cap, and at t equal to 4 it is equal to 48.0 I cap plus 3.50 j cap. So very simple to obtain the velocity at any instant or acceleration at any instant if you know the expression of velocity vector as a function of time or an acceleration vector as a function of time. Similarly, since the expression of position vector is also given, to determine the quantities which have been asked, the average velocity in the and displacement in, there is some typos here, displacement and average velocity in time interval t equal to 1 to t equal to 3 second. For that I have to determine the position vector at t equal to 1, which is obtained by substituting t equal to 1 in this expression, and the position at instant t equal to 3, which is obtained by substituting t equal to 3 in this expression. So the position vector at t equal to 1 turns out to be 2.00 I cap plus 1.75 j cap plus 3.14 k cap, and the position vector at t equal to 3 turns out to be, after doing calculation, 54.0 I cap plus 15.75 j cap 75 j cap plus 9.42 k cap, and that is because when you put t equal to 3, the t equal to 3, t cube is 27, and since a, b, c are given, so I have used the values of a, b, c also in evaluating it. So I have expressed the position vector in terms of a, b, c, and I get that t cube becomes 27, so 27 a I cap, and since t square becomes 9, so 9 b j cap, and since t is 3, so 3 c k cap is the value of position vector at t equal to 3 is described in this manner, and then I have used the values of a, b, c to arrive at these numbers. So doing such calculation is very easy. Once you know the two position vector, the position at instant t equal to 1 and at instant t equal to 3, you can find the displacement vector from the time interval 1 to 3 from the position vector at instant t equal to 3, subtracting out the position vector at time t equal to 1. That has been done here by using these two expressions which we have already have, and we can determine the displacement vector, which turns out to be 54 minus 2, which means 52.0 I cap, 15.75 minus 1.75, which means 14.0 j cap, and 9.42 minus 3.14 k cap, which means 6.28 k cap. So from this expression I get 52.0 I cap plus 14.0 j cap plus 6.28 k cap is the displacement vector for the time interval 1 to 3 seconds. And to obtain the average velocity, what I have to do? I have to divide it by the time interval. So it's very simple case here that the average velocity is obtained by the division of the displacement vector by the time interval, and so we get 52.0 I cap plus 14.0 j cap plus 6.28 k cap divided by 2, which is equal to 26.0 I cap plus 7.00 j cap plus 3.14 k cap as the average velocity. Now the next thing which I wish to discuss is about the frame of reference, and so that we can understand the relative motion. By now you have realized that in kinematics, whether we describe it in one dimension or two or three or any number of dimension, we have the position vector which cannot be specified unless we choose a formal system of a frame of reference. And we therefore say that the position vector is not absolute, but it is relative to a chosen frame of reference. In one dimension, we have chosen the frame of reference by choosing an origin and a direction, particular sense of direction as positive x-axis, and similarly later we discuss how we can generalize it to 2-dimension and 3-dimension. So by now you perfectly understand that choosing a Cartesian frame of reference involves choosing origin and choosing a set of axes. So in case of the 3-dimensional Cartesian space, you have to choose a set of 3 mutually perpendicular Cartesian axes. There can be other methods, other kinds of space description of the 3-dimensional space also, but right now I am restricting myself to discussion up to involving only 3-dimensional Cartesian space. But in any case, the position vector is not a quantity which is absolute, and by absolute I mean that which is independent of frame of reference, which has same value in all frame of reference. Like the mass of the particle, which we have considered for the particle as an intrinsic property, is an absolute quantity associated with the particle in the Newtonian mechanics. But position vector is relative and relative to a frame of reference. So when you describe and try to understand the motion of a particle in 1, 2 or 3 dimension, then you have to describe it in terms of position vector and other quantities, and all these quantities which we have defined are absolute or relative. That is an important question, and we have already understood that position vector is relative and so is its derivative with respect to time, which we have defined as the instantaneous velocity, instantaneous acceleration, and all other higher derivatives are also relative to a frame of reference. We have also realized that there are infinite different possible frames of reference, because in case of 3 dimension there are infinite points in the 3-dimensional space. Any point can be taken as origin, and similarly any direction can be taken as, in 3-dimensional space there are infinite directions. Only in case of 1-dimensional space we were having only 2 direction, but in 2 dimension and in 3 dimension we have infinite directions, and so any direction can be taken as the direction of x-axis. And then we have described that for 3 dimension we have to choose a plane, and in that plane we choose an axis which is at 90 degree anti-clockwise to the x-axis and call it y-axis, and the third direction z-axis is taken perpendicular to this plane, and the sense of direction of the z-axis will be given by right hand screw rule. I am repeating it so that you can remember it correctly. And if we have chosen a particular frame of reference and we have analyzed or solved the problem in that particular frame of reference, maybe somebody else has chosen the different frame of reference. So it becomes very important that there are infinite possible frame of reference, and if we know the information or the physics, or if we observe a physical phenomenon, theoretically we describe it by using a formal system of frame of reference, and since all experimental measurements are based on these quantities or definitions, so indirectly do involve the frame of reference. And therefore what I mean to say is that if I know the description of a natural phenomenon like motion of a particle in a one particular frame of reference, and then if I want to transform that analysis and description to another frame of reference, I must know transformation of kinematic quantities from one frame of reference to another frame of reference. All kinematic quantities which we have here introduced are vector quantities, and they would transform from one frame of reference to another frame of reference in similar manner, which we will discuss now. But it is very, very important, and these transformations, the kind of physical theories which we are building in the initial stage, are based on what we call Galilean Theory of Relativity. And therefore in Galilean Theory of Relativity, the transformations between frame of references would be called Galilean Transformation. I will explain it. Now, what is important one should understand is that if in one frame of reference a particle which appears to be at rest may have some non-zero velocity in another frame of reference. For example, you know that if you attach a frame of reference to the driver of the car, and if the car is moving with respect to you, but with respect to the driver, the car is always in the state of rest. So even if the car is moving with constant velocity in your reference frame, it is having no velocity in its driver's reference frame, and therefore the motion of the rest can be observed as the motion of uniform motion in another frame of reference. But it's not essential. If a frame of reference is explorated, then maybe it would also have a non-zero acceleration, which means that if the two frame of reference are moving with respect to each other with some acceleration, then the observation of the particle being at rest in one frame of reference would not mean that the particle in the second frame of reference would appear either in uniform motion or uniform acceleration. It may have non-zero velocity, non-zero acceleration, and non-zero higher derivatives quantity, and so on. It is also important, which you have realized by now, that we have to also choose origin of time. And let us make a default assumption that same frame of reference for time is chosen in all the frame of references which we will be describing. So that is why the time of reference in this initial discussions would not be given proper explanation every time, because let us assume that there is a universal choice of origin of time for all the frame of reference which we are interested in, and that choice of origin of time has been made, and time is now relative with respect to origin of time, but the time interval is absolute, and let us assume that the same specification of time would be used in all reference frames which we are considering, whether the having velocity with respect to each other or even acceleration with respect to each other. So whether the frame of references are moving with respect to each other with zero velocity or constant velocity or zero acceleration or acceleration. So in all cases, let us assume that all frame of references would employ same reference frame for time, which means same choice of origin of time, or that means the instant t equal to 0, and the time specification would be common. So each frame of reference, the time would be used in the same manner, and so we need not consider any transformation of time when we move from one frame of reference to another frame of reference. And when we make transformation from one frame of reference to another frame of reference, we would only consider the transformation of spatial dimension and not the dimension of time. So we wish to understand how kinematic quantities which we have defined can be obtained in the second reference frame from the first reference frame, or vice versa, which means from the second reference frame how we can obtain the set of kinematic quantities for the first reference frame also. So we will make use of vector algebra to understand the transformations, and our aim is to understand how one can describe motion in not only one frame of reference but in a set of frame of references. And the bigger question is whether there is a specifically chosen frame given by nature for description of laws of nature or not, or we have freedom to choose the frame of reference. In Galilean theory of relativity, we do believe that we have the freedom to choose frame of reference out of a given set of frame of reference, which I will define shortly, and this freedom would be exploited in description of physics based on Galilean theory of relativity. And whenever a choice is to be made, there can be different criteria, but the most common criteria for making choice is to choose a frame which is mathematically convenient for solving a particular problem. So there is no general frame of reference which should be used for solving all problems, but for each problem we may find a convenient frame of reference which is convenient to us mathematically for describing the motion. And if required, then once you know the transformation, you can transform the understanding from one reference frame to another reference frame quite easily. So let us consider two frame of reference denoted by the frame of reference S, and suppose if the picture is two-dimensional, so the frame of reference S, you have the x-axis and the y-axis and the origin, and let P be any particle point P, and its position vector is given by a position vector will be the vector starting from the origin to the point P, and it is being denoted by R vector at any instant t. Suppose R vector is, because at instant t suppose the particle is at point P. Then you can describe the particle's position vector by using this frame of reference S, and in this frame of reference S the particle would be described in this manner. But it is not essential. Let us consider another frame of reference S dash, and in this S dash frame of reference the position vector will be described by the vector starting from the origin of this frame S prime and ending at the point P. So in the frame of reference S prime, the position vector is being denoted by R prime as a function of time, will be a vector originating from the origin of the second frame of reference and ending at or terminating at the same point. So in both the frame of reference, we can describe the position vector of the particle in the manner shown here. The picture shown is of 2 dimension, but it can be generalized for 3 dimension also by drawing a suitable picture. And we now know that there are 2 origins, and let the position vector of the origin of the frame S dash with respect to a frame S, which means in the frame S the origin of the second frame S prime, which is called O prime, would also be having a position vector, and let that be described by capital RF vector. And therefore capital RF vector is also a function of time, because this frame of reference S prime may be moving with respect to the frame S, and it may also be constant, so we will consider all possibilities. But here remember, the position vector O dash, which is being denoted by RF vector, is also a function of time, and the position vector of the particle located at point P in the frame S, which is R, as a function of time, and the R prime, which is the position vector in the frame of reference S prime, is also a function of time. So all these three quantities are function of time. So here what one can understand is that this is a frozen image, or it is a snapshot taken at a particular instant t, and that instant the diagram, it makes very clear that from the vector algebra which we have discussed and learned earlier, that what you can write that this vector O dash plus O dash P is equals to the vector OP, and that is being described here alternatively, that R dash T is O dash P. So R dash T is O dash P is O dash O plus OP, O dash O, O dash O plus OP. But O dash O is minus RFT, so we can write that R prime time as a function of time can be obtained from R prime is equals to minus RF plus R prime. So this is the first transformation, and I would express and write it in this manner. Therefore R prime vector is equal to R vector, which is the position vector in the frame S, minus the RF vector, which is the position vector of the origin of the second frame with respect to the first frame. So this is written here, R prime is equal to R minus RF vector, and then by differentiating this we get the differentiation of R prime with respect to time is denoted by the velocity vector in the frame of reference S dash, and which is denoted by V prime, and the differentiation of V prime is being denoted by acceleration A prime. And similarly, so in the frame of reference S dash, we have position vector given by R prime, velocity vector given by V prime, and acceleration vector given by A prime. And the frame of reference S, the position vector is R, the velocity vector is V, and the acceleration vector is A. But the kind of mathematical analysis which I have explained using this picture from the vector algebra, it is clear that the two quantities are related in frame of reference 1 and 2. The quantities are related by these three relations. We are here limiting ourselves up to the acceleration, but similar relations can be written for the higher derivatives like the jerk, snap, crackle and pop. And so remember, you can generalize it if required to include those higher derivatives also. But confining ourselves to the quantities up to acceleration only, the three relations are given here. And these three equations tells you that if you know RF as a function of time and VF as a function of time, you can obtain by differentiating it with respect to time, and the acceleration as a function of time you can obtain by differentiating the VF with respect to time. And so if you know these quantities, so it means that if you know RF as a function of time, then you can transform the information, suppose given in the frame S, you can obtain the information in the form S dash. And because these are algebraic equation, you can also write equation in such a manner that you can obtain from the information given in the frame S dash the relative information in the frame S also. So these are called Galilean transformation between these two frame of reference S and S prime, which have been chosen here. And remember, each of the quantities, velocity, position and acceleration I am using here, is a function of time, and therefore at any particular instant of time the relationship would be understood in terms of in these equations which we have given here. Now suppose Rf upon is a constant and doesn't depend upon time. So the position vector of the frame, second frame, with respect to the position vector of the prime frame with respect to the position vector origin of the unprimed frame. So I will call prime frame and unprimed frame. So the position vector of prime frame with respect to origin of unprimed frame is given by Rf vector, and suppose it is independent of time. That means the two frame of reference, the origins have at different locations, but they differ only by a space translation. So they have been displaced. So Rf is suppose given as a constant of time. Then definitely Rf doesn't depend upon time. So Vf and acceleration Af and all other hard derivatives would be 0. And that would mean to say that if you consider two frames which are related to each other by mere space translation, that they have parallel axes and only the space have been translated, so origin is at a different point, then what you will find that the physical quantities from this relationship, Rf is not constant and all these Vf and Af and higher derivatives are 0. So you find that velocity and acceleration will have behave like absolute quantities, which means will have same value in the two frame of reference, but the position vector will not be same because Rf is not equal to 0. So the case has been explained. Now suppose Rf is a function of time in such a manner that when you find its derivative, then the velocity of the frame as the prime frame with respect to the unprimed frame, so that is being denoted by the velocity Vf vector, which is given by the rate of change of Rf vector with respect to time, and suppose this is a non-zero constant, so but it's constant, so velocity is constant but its derivative is 0, therefore acceleration will not transform, acceleration would behave like absolute, but the velocity will get transformed from one reference frame to another reference frame. But remember, it's not necessary that Vf, the velocity of the prime frame with respect to the unprimed frame, should be constant. It can be changing, it can be accelerating, and it can have any value of acceleration. So in general, the Af or even higher derivatives will have non-zero constant values and maybe time dependent values. But another case which we can consider is the specific case when the acceleration is constant. So there are many cases which are possible now when we say that the position vector Rf is constant, or the second case when Vf is constant, the third case when Af is constant, fourth case when jerk similarly obtain Jf and that is constant, and so on. Many other cases can be considered. In general, none of this special case should hold, and so Rf should maybe such that the values of Vf, Af and higher derivatives are not constant. But in our course of discussion, which we will be taking up shortly for describing the Newton's laws of motion, we find that the frame of reference which we call inertial frame of references are very important. What is an inertial frame of reference? In fact, this term should be used for a set of frame of reference. So here we have described so far only two frame of reference, as unprimed and as primed. So as unprimed and as primed, two frame of reference would be called inertial frame of reference if they are such that the Af is 0, and which means that the two frame of reference are moving with 0 or constant velocity with respect to each other. In that case, the transformation equations would reduce to, since acceleration would be having same value, because Af equals to 0, so acceleration will have same value and will the frame of references, and since Af has become equal to 0, the higher derivatives of Af would also be 0. So what I am saying for acceleration, That would also be true for jerk, snap, crackle and pop or further higher derivatives if you wish to define. But in the inertial frame of reference, the position vector and the velocity vector will get transformed. So a set of frame of reference may involve more than two frame of reference, but out of the set, if you choose any two frame of reference, then this kind of relationship will hold, that every frame in this set is moving with either zero velocity or with constant velocity with respect to any other frame in the set. So from the set you can choose any two frame and the description which I have given here would be holding. That means that the velocity of prime frame will be constant with respect to the velocity with respect to the unprimed frame, or without using the primed or unprimed, if the velocity of the first inertial frame of reference would be constant when it is described in terms of the second frame of reference, so vice versa. So if you choose the AF by choosing the first frame of reference, then that is 0, or whether you choose the AF by choosing the second frame of reference for describing the origins in relation to each other, in each case this will hold true. So what we find, that inertial frame of references, we have this particular simplicity that the position vector and the velocity vectors transformations are important, but all other higher derivatives will have same value in all the inertial frame of references. And if you know the position vector and velocity vector in one of the inertial frame of reference, you can compute the position vector and the velocity vector in the other frame of reference by using this relationship. And for higher derivatives, since these are constants, will be having same value in all inertial frame of reference. So the set of inertial frame of reference is help us in reducing the important Galilean transformations to the two relations, the relation for Galilean transformation of position vector and the velocity vector. And for all other higher derivatives, the values are same in all the inertial frame of reference. Now let us consider this as an example, projectile motion described in two inertial frame of reference. Consider a frame of reference S in which the projectile is launched from the ground with the projection speed u and the projection angle theta as discussed earlier in the projectile motion. And let us choose another frame, and now we choose the another frame in such a manner that it was having the origin same with the frame S. So S prime was having origin coincident at time t equal to 0 with the origin of the frame S, but it is having a velocity with respect to the origin of frame S, and that is given by constant velocity is given by u cos theta I, where u cos theta is the projection of the projection velocity along the chosen x-axis. So you find that the frame S dash is moving with the same horizontal velocity as the particle which is being projected, launched from the ground in the frame of reference S. So I have chosen S prime specifically to have this VF. And now we can discuss, since acceleration is same in all frame of reference, in the problem from we have already discussed for frame S. So I have written all the expressions here, and acceleration in the frame S is given by minus g j cap, and I am using that the axes are parallel, so the same unit vector for frame S and frame S dash. So x, y axes which we have chosen to describe projectile motion, we assume that the axes in S and S prime are same, parallel to each other, so same unit vectors is being used here. So acceleration in the frame S is given by minus g j prime cap, and similar expression holds for the frame S prime. But the velocity will be different because we have derived earlier that the velocity vector in frame S would be given by u cos theta I cap plus u sin theta minus gt j cap, and this expression in the frame S prime can be obtained now by using our transformation relationship, that V prime will be V minus Vf prime, and since Vf prime is given as u cos theta I, so this term u cos theta I gets cancelled, and you have that in the frame S dash it is having velocity only along the vertical direction, and in the frame S it is having both horizontal and vertical component of the velocity. Similarly, for the position vector, we can further discuss that it can be obtained by integrating it, and we have derived earlier this relationship, or we can find the prime position vector by using that transformation law. And since Vf is given by u cos theta I cap, the Rf vector can be obtained by integrating it with respect to time, and we will get that relationship ut cos theta I. So what I have done, I have subtracted ut cos theta I cap from this relationship. So r prime is also ut sin theta minus half gt squared j cap, which means there is no change in the x coordinate or x component of the velocity is 0. There is no change in the x coordinate, and case of the frame S prime, and in the case of frame S, both x and y coordinates are changing as described here. The equation of trajectory which we have obtained earlier is a parabola in the xy plane. Here there is no motion along the x-axis, the only y coordinate is changing, and therefore we can say that what the observer having the frame S and using the frame S as a formal system for describing the phenomenon, he will find the trajectory to be a parabola, but the another observer who is using the frame S prime would say no, it is not moving along a parabola but along a straight line. In fact, straight line is also a special case of parabola, but here I am making a difference between the shape, that in case of frame S both x and y coordinates are changing, but in frame S prime only the y component is changing, the motion is taking place in the y direction only, and so it's a one-dimensional scenario for S prime and for S. So what we find that it is very interesting, if we describe the phenomenon of the projectile motion in the frame S prime, the phenomenon becomes one-dimensional or describable in terms of one-dimensional description, which we have discussed earlier. The frame S involves two-dimensional description essential, because the velocity vector is having both x and y component, whereas in the frame S prime the velocity vector is having only y component, and that's an interesting thing which makes you understand and help you understand the fact that choosing a frame of reference is also very important in analyzing or solving any problem of motion using kinematics, because if you choose the frame of reference in such a manner that the motion is taking place in one dimension, the mathematics will definitely be simple and would be convenient. So what I say, that if we describe the same phenomenon in frame S prime, then that is easier in this particular example. In different example, the different cases shall be examined in the same manner by using the same, then any of the frame can be used. But both the frame S and the frame S dash, the motion is having same value of acceleration, and it is a case of uniform acceleration in both the frame of reference. Because the two frame of reference are inertial frame of reference, they are moving with respect to constant velocity with respect to each other. This is true. If another frame of reference S prime is so chosen that Vf is not constant, then this will not be true, and in the frame S prime, or even if in the frame S it is having no acceleration, or sorry, it is having constant acceleration, in the frame S prime it may have a time dependent or varying acceleration. So relative description of motion using frame of reference is very important. Now, can there be a frame of reference which we can consider as in absolute manner as inertial frame? or which we can say that if you choose this particular frame of reference, it would be inertial. As I explained, the term inertial frame of reference makes only sense when you compare or when you have two frame of references or a set of frame of references. But let us consider a frame of reference which is attached to Earth. Now, in most of our discussion later also in this series, till we discuss the Newtonian physics only, we will assume that the frame of reference attached to the laboratory or to the Earth would be considered as an inertial frame of reference. However, we know that Earth is rotating about its own axis and it is also revolving around the Sun, and therefore it is wrong to consider it as an inertial frame because it is having some acceleration, and the circular motion, uniform circular motion, we have discussed earlier that in uniform circular motion the acceleration is involved and is not constant and is changing its direction at every instant of time. So the same holds here, that the Earth is an accelerated frame of reference. So is the Sun. In fact, if you attach your frame of reference to any point in the universe, since everywhere the gravitational field is existing because of the cosmic objects, massive objects which we have. For example, we know that Sun is also revolving around the center of galaxy, and so on. So because of the gravitational field, any particle which is having some mass would experience, later we will describe a force or experience therefore an acceleration. Gravitational field is a measure of acceleration. So there is no point to which we can attach a frame of reference in true sense and call it inertial. So the concept of inertial frame of reference is based on assumption. So in our discussion we will assume that any frame of reference which is moving with constant velocity with respect to the Earth, the laboratory frame of reference which we have chosen, and that will be taken as inertial frame of reference. However, the frame of reference attached with the Earth is a non-inertial frame of reference because it is having acceleration. Later in the series, we will also discuss how to consider the effect of non-inertial frame of reference because Earth is rotating about its axis. What kind of influence it would have on free fall or projectile motion, that we will consider later in this series. So far we have not considered it, and this non-inertial effect I have said earlier also that we are not considering. And however, when we will consider the non-inertial effect for free fall from say height h equals to 10 meter, then we will find that the effects are quite small, and therefore it is justifiable to first develop an understanding based on the assumption that the frame of reference attached to the person standing on the ground observing the free fall or projectile motion is an inertial frame of reference. And another frame of reference that corresponding to that particular person standing on the ground, if somebody is moving in the car with a constant velocity with respect to the person standing on the ground, would also be a inertial frame of reference, because any two frame of reference which are moving with respect to each other with constant velocity can be called inertial frame of reference. So we find that the approximation, the concept of inertial frame of reference now may be correct approximately only in some cases, but it is a useful concept. And so in most of our discussion in coming lectures related to Newtonian physics, we will assume that we are considering the set of inertial frame of reference. All the frame of reference involved in discussion are inertial frame of reference with respect to each other, and unless otherwise specifically mentioned, we will not consider a frame of reference to be non-inertial. But if it has been specifically mentioned in a particular case, so that would become a default option. So we prefer this particular set of frame of reference out of the infinite frame of reference. Every frame of reference may not be inertial, but we limit ourselves to the frame of reference which can be considered as inertial frame of reference for our discussion. In the principle of Galilean relativity or principle of relativity, which is common also in the special theory of relativity, and that we call principle of Galilean relativity, is that laws of physics have same form in all inertial frames of reference. So if you choose a set of inertial frame of reference, then laws of physics will have same form in all the frame of reference. So in other words, laws of physics which you observe to hold true in any of the reference frame, they would also hold true in the other inertial frame of reference from the same set. So without bothering about it, you can make this conclusion based on the principle of relativity. I have already emphasized earlier in the initial discussion that there are certain principles which we can assume in the development of a physical theory, and those principles are, since assumptions will not be proved, will be just assumed or taken granted. So when I say principle of Galilean relativity, I am taking it granted that nature is such that, let us assume, which is not true in fact, because later we will have to consider other form of relativity, but let us consider that the principle of Galilean relativity holds, and which means that laws of physics have same form in all inertial frame of reference. If laws of physics which you have obtained and checked in one particular frame then to hold true, then in all other inertial frame of reference these laws of physics would also hold true. And therefore all frame of reference from this set of inertial frame of reference are equivalent as far as describing the laws of physics are concerned. So you can choose any frame of reference to describe the laws of physics out of the set of inertial frame of reference. A state of uniform motion in a particular frame of reference will appear, as explained earlier, state of rest in a specifically chosen inertial frame of reference which is moving with a specific velocity. So state of uniform motion which is appearing in one frame of reference may appear as a state of rest in another inertial frame of reference, and therefore in the light of principle of Galilean relativity it becomes clear that the state of uniform motion and the state of rest belongs to the same laws of physics or describe the similar thing or do not involve different laws of physics. So a state of rest in one frame of reference thou may appear as a state of uniform motion in another frame of reference, but it is not involving different physics, or we can say that the state of rest and state of uniform motion are equivalent to each other as far as the relativity or Galilean relativity is concerned. Galileo Galilei first described this principle in 1632 in his publication Dialogue Concerning the Two Chief World Systems. Using the example of a ship traveling at constant velocity without rocking on a smooth sea, an observer below the deck, he said, would not be able to tell based on observations whether the ship was moving or stationary. So Galileo Galilei carefully observed and concluded that if a ship is traveling with constant velocity without rocking on a smooth sea, then the person who is below the deck would not be able to discern or know whether the ship is in the state of rest or in the state of uniform motion, and thus the two are equivalent, and that is the conclusion. However, on that basis he proposed what we call the principle of Galilean relativity. But the state of uniform motion and the state of rest are manifestation of same laws of physics, but the states are different than the case of uniform acceleration, which means that the state of uniform motion cannot be transformed into a state of uniform acceleration in another frame of reference. So if something is having uniform acceleration in one inertial frame of reference, it will also be having uniform acceleration in all other inertial frame of reference, because as explained earlier, the acceleration is same in all inertial frame of reference. So we say that the state of uniform motion and state of rest are equivalent to each other, but neither the state of uniform motion or nor the state of rest is equivalent to the state of uniform acceleration. The state of uniform acceleration therefore definitely involve different physics than the physics involved in the state of uniform motion or the state of rest. And that we would be able to understand by developing the ideas further and developing what I call or understanding Newtonian physics, what has been given and specified by Newton's in terms of his laws of motion and including the law of universal gravitation. So we would consider it in coming lectures that the state of uniform acceleration would appear as the state of uniform acceleration in all inertial frame of reference, but is not equivalent to the state of uniform motion or the state of the rest, by which I mean that if a particle, for example a projectile which has been projected with some projection velocity in a particular frame of reference would always be having acceleration in all other inertial frame of references also, and you would not be able to reduce the projectile motion under uniform acceleration to a projectile motion with zero acceleration except a suitably chosen accelerated frame of reference, but not in the another inertial frame of reference. And since we are limiting ourselves to the inertial frame of reference, so we can say that the projectile motion which involves acceleration due to gravity would involve acceleration due to gravity in all inertial frame of references. And so the acceleration due to gravity would be same in all inertial frame of references. And however, if the acceleration is non-uniform in one of the inertial frame of references, it would also be non-uniform in all other frame of references and will have similar behavior with respect to time. Definitely, this will not hold true if the frame is an accelerated frame or non-inertial frame, and I am reminding just that. Now let us consider few applications of the relative motion. One is the Bott river problems, that let the velocity of Bott relative to the still water. If water is not flowing, then say the Bott can or the boatman can row the boat with this particular velocity, which I am denoting by v vector bw. vbw, so Bott to water. So velocity of Bott with respect to the water would be denoted by vbw, Bott with respect to water. So that of the water flow in the river with respect to the person standing on the ground, so that let me denote by vwp. So velocity of water with respect to the person, velocity of Bott with respect to the water. So I can find the velocity of the Bott with respect to the person very easily by using the vector algebra, and velocity of Bott with respect to person vbp will be equal to vbw plus vwp, because bw plus wp just by the displacement vector algebra which we have discussed earlier, vector algebra. So it becomes very clear that the velocity of Bott with respect to the person standing on the ground can be obtained if you know the velocity of Bott relative to the still water and if you know the velocity of the flow of water. So by adding the two velocity, so it is kind of addition of velocities involved, we can obtain the VBP. Now these some specific cases of the motion of Bott in the river. One is called downstream motion. We call it downstream motion when the velocity of Bott with respect to the still water is also in the same direction as that of the water flow. So if the boatman is rowing the boat in the same direction in which the water is flowing, then that motion is called downstream motion. Here in this picture I have taken the flow of the stream towards this left direction, and so if you row the boat towards this direction, then that would be called the downstream motion of the boat. And since the two are having the same direction, the velocity of boat with respect to the water and velocity of the water with respect to the person, so in the same direction you will get a higher speed, and you say with respect to the person. So VBP will be obtained by the adding the two. So you can say the speed with respect to the person standing on the ground. Somebody is standing here, suppose, then the speed of the boat with respect to that person standing on the ground would be equal to the speed of the boat with respect to the water plus the speed of the water flow. Upstream motion is against the stream or upstream motion. So if the water is flowing in this direction and you row the boat in the opposite direction, then that is called upstream motion. Upstream motion, the direction of unit vector of BW and WP would be opposite to each other, and therefore the speed VBP will be equal to the difference of the two. And in that case, you would be able to move the velocity, or upstream motion would be possible, and you would be able to go in the upstream direction only when the VBW is greater than VWP, which means the velocity with which you can row the boat is greater than the velocity of the water flow. But if you can't row the boat with that velocity greater than the velocity of the water flow, then there will be a drift in the downstream and you would not be able to get a displacement in upstream direction. So when a river is flowing, there are two directions: downstream direction, the direction of flow; upstream direction, the direction against the flow. And here I am considering the motion of the boat in this particular slide along the either parallel to the flow of the stream, so either parallel or anti-parallel. And when the two are parallel, the VBW and VWP, we call it downstream, and when the two are anti-parallel, then we call it upstream. Now motion across the river can also be considered. So suppose this direction, which you call the direction of the river flow, is x-axis is chosen, then the across direction would be described by the y-axis, and you can consider it as a two-dimensional problem. So if VBW is at 90 degree to the VWP, which means if the velocity with which you row the boat is at 90 degree with respect to the water flow velocity, then what will happen, that suppose the width of the river is W, because the two velocities are in 90 mutually independent direction, so you would be able to reach the other side of the shore. So if you start journey from this shore, then you can reach the other shore just by traveling and having the VBW in this vertical direction. Then the time taken in the crossing will be equal to the width of the river divided by the VBW. But remember here, VBP will not be in this direction and there will be a drift involved, because you are maintaining the rowing the boat in the vertical or in this direction, y direction, across or parallel to the width direction. So when you are rowing the boat in this direction, then what you are getting, because of the downstream velocity of the water or velocity of the water flow, there would be a drift, and the drift would be equal to the time taken in crossing the river into the river flow velocity. So one can cross the river by rowing the boat in this particular direction, but you will not be able to reach the point directly opposite to the point of start. So this is the point of start, and the directly opposite point you will not be able to reach, and you will get certain drift. If you want to make drift zero, then you have to row the boat at a particular angle. So what we assume, that suppose that it is happening in such a manner that not the VBW is at 90 degree to the VWP, but VBP is in this direction. So the net velocity is in this direction, and when net velocity is in this direction, VBP, then we know that VBW is not in this particular direction, and because VBP is equals to VBW plus VWF, I can write that VBW is VBP minus VWP, and therefore from the mathematics, since the two are at 90-degree angle to each other, one can show that VBW would be having a value, or VBP will be having a value which is given by these equations. So in this case, the VBW square minus VWP square is involved. So remember that the time taken in crossing would be given by the width of the river divided by the speed as measured by the person standing on the ground, which means the magnitude of VBP, and that time would not be the minimum time because VBP would definitely be less than VBW because of this relationship. So from above two cases, we conclude that the shortest time in this particular situation, if we ignore the drift, then the shortest time you can cross the river. If you row the river or boat, if you row the boat in the direction 90 degree to the shore, then you can reach the other side or other shore in the minimum time. But if you want to have a zero drift and reach directly to a point which is exactly opposite to the point of start, then you have to row the boat at a particular angle, and that is being described here by this mathematical relationship. But you row it in such a manner that VBP is along this direction perpendicular to the shore. Questions can be considered for such cases, and I give you one example. A child in danger of drowning in a river is being carried downstream by a current that has a speed of 2.5 km per hour. The child is 0.600 km from shore and 0.800 km upstream of a boat landing when a rescue boat sets out. So rescue boat is in a point which is away from the location of the child. The child is 0.6 km from shore. So in that direction, if you call J direction, then it is at 0.6 J, and from the particular point from where the boat will start and proceed. So 0.6 J as I have given here, and the 0.8 K. So I have chosen this direction, the upstream direction, as the I, because it is given here that the child is 0.6 km from shore and 0.8 km upstream of a boat. And upstream I am taking as plus x-axis, downstream I am taking as minus x-axis in my analysis of the problem. If the boat proceeds at its maximum speed of 20 km per hour relative to the water, what heading relative to the shore should the pilot take? Question number 1. Question number 2, part 2, B. What angle does the boat velocity make with the shore? And part C, how long does it take the boat to reach the child? And this question I have taken from Holiday Resnick Walker. So credit is given. So at time t equal to 0, from the given information I can write that the position vector of child with respect to the boat at time t equal to 0 is 0.8 I, converting the upstream direction as I cap, and 0.60 K, this particular direction from the starting point, as J direction, so 0.06 J km. Now what is given? That the velocity of water is given, river flow, and that is 2.5. So I have written here 2.5 km per hour, but water is flowing downstream, so minus I cap. So that is given. What is further given? That the boat can be rowed with the maximum speed given by 20 km per hour. So that I have mentioned here, that this maximum of the VBW is 20.0 km per hour. And now to solve the problem, as the boat and child both will be drifted downstream by the same velocity VWG, and therefore the boat should be initially given velocity with respect to the water in the direction which was initially the RCB direction. So interestingly here, the RCB vector which I have shown is a unit vector, and so is the same thing is unit vector, because you can check that the magnitude of this vector is unity. 0.8 square plus 0.6 square will turns out to be 1, and so what we find that the bot should be rowed in this particular direction. So initially when the botman starts the row, he looks at the position of the child and to that particular direction he would be rowing the bot and ignoring the the flow of the water, because the flow of the water is common to both. But remember that he is to move upstream, because in that direction is the boy, and that's why I have given the analysis in that manner. The downstream direction is minus I cap. So VBW would be in this direction, and since the maximum VBW is 20, so I choose maximum, and so I choose this particular direction, and then I find that what is the direction? This is the direction, and this direction, the unit vector should be, can be written as cos theta BW I cap minus sin theta BW j cap, or this should be the plus. There is a typos here. Remember, make a correction here. Earlier I thought that I would choose minus j as a direction, so there is a typos. So plus, so cos theta W I cap plus sin theta BW j cap. So I find that cos theta BW is 0.8 and theta W should be. So the question number A, the answer is 36.9 degree, because the answer we have obtained on the basis that he should row the bot in the direction initially at time t equal to 0, the RCB direction he should row the bot, because the drift will be common for both the child as well as the bot. And now the next part is that what angle does the bot velocity makes. So I have chosen the maximum velocity 20 because it wants to reach the bot, wants to reach the child as early as possible. So rowing at the maximum. So what is VBW? So 20 and this RCB direction. So 0.8 I cap plus 0.06 J cap and plus VWG, which is minus 2.5 I. So what is the velocity of bot with respect to the ground? Velocity of bot with respect to the water given by this. Velocity of water with respect to the ground given by this. So I finally get 20 into 0.8 is 16I minus 2.5I. So 13.5 I cap plus 12 J cap. So remember, the VBW, velocity of bot rowing with respect to water, is 16 I cap plus 12 J cap. But the velocity of bot with respect to the ground is 13.5 I cap plus 12 J cap, because bot is moving in the direction against the stream, and so it is being is facing motion against the water flow, and so VBG is given by this 13.5 I plus 12 J. From this you can find again the angle tan theta W, and tan theta BG can be obtained from the y component divided by the x component. Y component is the 12, x component is 13.5. So tan theta BG is 12 divided by 13.5 is 0.8 at 9. And hence theta BG, if you find the tan inverse of this particular angle, will turns out to be 41.6 degree. And time taken in reaching, and since the y component direction you can consider here to easily find the time taken, the displacement in j direction required is 0.6 and the velocity in the j direction is 12, so it is 0.6 by 12 hour or 0.05 hour, and you can convert it into minute by multiplying by 60. So 3 minutes is the answer. Similar analysis can be done for the questions related to airplane and wind. So wind is blowing and the airplane can get a particular velocity with respect to the still air or air speed, and then the net speed of the airplane as observed by an observer from the ground. So let velocity of the airplane relative to air be velocity of plane relative to air. I have denoted by VPA, magnitude of which I am calling the air speed, and the velocity of wind flow with respect to the ground by VAG. Then the velocity of the plane with respect to the ground can be obtained by adding the two velocity of the plane with respect to air plus velocity of air with respect to the ground. Now there are various ways of solving questions, but generally the information is given by using the angle as described and by using east-north direction in XY plane, and the vertical upward direction we can take as K direction. So let us choose magnetic east direction to be x-axis, magnetic north direction to be the y-axis, and vertical upward direction to be the z-axis in solving such numerical questions involving airplane and wind relative motion. We can specify these quantities by resolving along this Cartesian axis. Remember that the navigation directions are usually expressed in terms of compass angle in numerical question, and so you have to convert it into our notation. In navigation, the heading of the airplane, the compass direction in which the airplane's bow or nose is pointed is shown, and the compass directions are shown in such a manner that the due north is indicated by 0 degree, due east by 90 degree, due south by 180 degree, and due west by 270 degree. And since we have chosen the direction with respect to the x-axis, and we have chosen x-axis in this particular direction, so the our angle, in my notation which I am being making, x-axis in the due east direction, y-axis in the due north direction, it is very easy to understand that if you know the compass angle, then you can get the angle which have to be used in my notation, and that is by simply subtracting out the compass angle from 90 degree. So if something is given in the compass 90 degree, then that will mean 90 degree minus 90 degree, which means 0, and it is due east. And similarly, the due north will mean that 0 degree compass, and so 90 degree minus 0 in my notation, due north is 90 degree, and due west is 180 degree in my notation, and it is 270 degree in the compass. So it can be obtained from 90 degree minus 270 degree is minus 180 degree or 180 degree, whatever you call. So you can express it in terms of the theta. In my understanding, the theta can be, we have earlier explained it, that velocity of the plane with respect to the air can be given by VPA cos theta I cap plus sin theta j cap, where theta are being used by using this notations of XYZ axis, and the VPA can also be written by using the theta compass. So by replacing theta by 90 degree minus theta compass, cos of 90 degree minus theta compass is equal to sin theta, cos 90 minus theta is sin theta, and similarly sin 90 minus theta is cos theta. It has been used here in solving this problem. Numerical questions can be solved. For example, in this question, a live plane attains an airspeed of 520 km per hour. The pilot sets out for a destination 930 km to north, but discovers that the plane must be headed 18 degree east of north to fly there directly. The plane arrives in 2.10 hour. What was the wind velocity? So wind velocity is in question. What is given? The live plane attains an air speed of 520 km. So velocity speed of the plane with respect to the air is given as 520 km per hour. Angle is given, and since angle is given 18 degree east of north, so which will mean 72 degree to east, and therefore I can also, what is given, that VAG, the velocity of the airport, because it takes 930 km north, it covers in the time interval 2.10, so you get this, the velocity, the net velocity, which AG, the speed is given by 930 by 2.10, and which turns out to be 443 km per hour. Now this is the information given, and I can write VPA as VPA cos theta I plus sin theta j. VPA as given 520, so cos theta or cos 72 is 0.309, sin 72 is 0.951. So I have substituted and expressed the VPA in vector form. VPG, because is in the j direction, because the destination is in the north direction, so VPG is 443j, and 443 the speed is been obtained because it takes 930 kilometers to be covered in time 2.10 hour, so I get 443 kilometer per hour, and this is also in kilometer per hour. And now to find the velocity of the air flow, so that is by using that relationship VPG equals to VPA plus VAG, I can write the velocity of airflow with respect to the ground can be obtained by subtracting the velocity of plane with respect to the air from the velocity of plane with respect to the ground. And so I do the mathematics here. The VPA is given as here, and VPG also is given. So by subtracting, we get this as the answer of the velocity of air with respect to the ground, and that is 161 I plus I cap plus 52 j cap. So in this direction the air is flowing. So such numerical questions can be solved very easily. The two more questions I am giving here. The pilot of an airplane notes that the compass indicates a heading due west. So theta compass is due west, and so which means as I have explained earlier, west is due west means 270 degree. The airplane's speed relative to the air is 150 km per hour. If there is a wind flows which is happening at 30.0 km per hour towards the north, find the velocity of the airplane relative to the ground. So what is given to you? Velocity of plane with respect to air is minus 150 I because it is due west, so minus 150 I, and velocity of AJ is the due north, so 30 J. And so you have to obtain the velocity of plane with respect to grounds, just add this to velocity, and so that is the answer, minus 150 I plus 30 J cap. So very simple question. Another question, a bolt drops from the ceiling of a train car that is accelerating northward at a rate of 2.50 meter per second squares. And what is the acceleration of the bolt relative to the train car and to the earth? So now this is a general question of the Galilean transformation. So it is given that the acceleration of train with respect to the earth is 2.5 j because northward, so 2.5 j meter per second square. And as a bolt drops from the ceiling of the train car, it is not being accelerated just after drop, and so by the acceleration of the train which is having with respect to the ground, acceleration of the train with respect to the earth, it is not being, and but will have the same initial velocity which was the train having at that time. So after the bolt starts drop from the ceiling, it gets disconnected to the train, and so it's not having the same acceleration as the train is having, but the bolt starts the journey with the same speed which the train is having in the horizontal direction. So the acceleration, because the two frame of references, the frame of reference, the train car that is accelerating northward at a rate of 2.50 meter per second square, a frame of reference attached to the train car can be considered, and a frame of reference attached to the earth can be considered. With respect to the earth, the acceleration is minus 9.8 vertically downward, which I am taking as minus k direction. So now what will be the acceleration with respect to of the bolt with respect to the train? It will be the acceleration of bolt with respect to the earth and plus acceleration of earth with respect to the train, you can say, or you can subtract out the acceleration of train with respect to that. Acceleration of train with respect to earth is given as 2.5 j, and that of the bolt with respect to the earth is given as minus 9.8 k. This is the answer, therefore, that what acceleration it is having with respect to the earth, minus 9.8 k, and what acceleration it is having with respect to the car, so with respect to train. So that is the second answer. ABT is minus 2.5 j minus 9.8 k. So this is to conclude. Today we considered a set of numerical questions, but there are many numerical questions related to kinematics which are very interesting and which I wish to cover in my presentation. And so the next talk would be devoted to numerical questions of kinematics. Some interesting numerical questions of kinematics will be discussed. And in the next to next talk, we will take up Zeno, Aristotle, and Galilean point of view about motion, the philosophical ideas which Zeno, Aristotle gave, and the Galileo's ideas on motion, and the Newtonian ideas, and so as to develop the framework which we call Newtonian mechanics based on Newton's laws of motion. I hope you are liking my video series. Please click the like button if you like this talk, and you can subscribe my YouTube channel by clicking the subscribe button. You can click the bell icon to get the notification. Thank you for being with me in this video lecture series.